So Akshay had asked this question last time, that this factorization theorem. So the proof I presented was a little bit indirect, in the sense that, so we constructed a map like that, and it goes down to the space of Vancouver, and we proved that it's surjective. And then to prove that it's injective, I took the dual map and proved that that also is subjective. And what Akshay suggested, that maybe we should try to find a splitting directly here and not have to go to the dual map. So, I mean, finding a splitting will be more natural way to deal with this. But what I was just saying that, so this was the factorization map. And if I use the propagation theorem, then this becomes the factorization map. And now there is a kind of a canonical map here. So if I take H tensor, let's say some vector, I'll just write it W mu in whatever. So I take arbitrary vector here, and we want to get to here. So what we will do, so you see, this is the unique gene variant here. So I mu is the unique gene variant in one of the factor. So let's take, so any element I can write here as H tensor. Okay, so Z mu I mu plus something, and I will just say W mu prime. Okay, so let me explain this. So you see, since this has a unique gene variant, any gene variant in the direct sum can be written as summation Z mu I mu, where Z mu is some scalar. That will be an arbitrary gene variant. And now I'm taking the perpendicular to that. Everything which is not a gene variant. And now I will just map this thing to H tensor summation Z mu. I mean, not tensor, but a scalar. I would map this. So clearly, at this level, it splits. Clearly, it splits at this level. But somehow this map does not seem to go down.
Right.
Yeah. So one has to do a little bit, something slightly more subtle, which I did not think too hard to do. So anyway, but it's a, yeah. It's a very interesting and natural question. Okay, so let's get back to.
Shravan, in your, has G always been semi-simple?
Simple.
Simple even.
Yeah, see, because I am taking the corresponding affine Lie algebra. And I mean, you can work out the theory for semi-simple also. It will be.
I was actually more wondering if you could take G to be a torus, even you.
No. There is some issues there.
Oh.
Yeah. So reductive, you are asking.
Yeah,
even to torus.
Torus, yeah.
Right. So
I'm not saying it's very interesting, but I'm just
no. Actually,
it go through or not.
No, see, you have to be you have to be a little bit careful about that. So see, so far I have not presented the theory for the group side.
Yeah.
Now, if you take the group for the torus, or the flag variety for the torus, it's not reduced.
It's not reduced.
It's not reduced.
Yeah. But still you can.
I mean, you could talk it.
It still has some kind of
scheme.
Yeah.
In this scheme. That definitely makes sense in this scheme.
Yeah.
But so many of the things do break down. I mean, breakdown means you have to be very careful about the generalization to the reductive situation. So right. So at what point we have crucially used the simple of the Lie algebra. So
And you cannot have factorization, right? Because
yeah, right.
the category is not the representations.
Yeah, right. So
You don't have factorization.
I think that's a.
So you see, so the question is, okay, so let's take representation theory of this one. Okay, even the central extension so yeah, see, even the central extension will create a problem. And the region H yeah, I am not sure if the central extension
Okay, it's not so important. I just
actually it is important. I tell you that. So forget about reductive. Let's take semi-simple, but let's take non-simply connected group. And the theory, you have to be very careful about that. So already there's a problem there. I mean, some people have worked out some formula, but there is already an issue there. That if you take a non-simply connected group, I mean, basically I'm taking simply connected group in the disguise because I'm taking the weight lattice, not the root lattice, for example. So if you were to ask, what about if I take the adjoint group? And see, in that case, see, I think, unfortunately, I would not have time to do the corresponding, the group aspect of the theory. So what happens that if I take the infinite Grassmannian, let me tell you this. So if I take the infinite Grassmannian for a semi-simple group, but not necessarily simply connected, then it's not connected. It has several converters. So now see, when you are, see, there is a completely parallel theory for at the group level, okay? Now, so there it has several components. So you have to work component-wise. On each component, you have to work out the detail. So that's why, I mean, the simply connected theory is simpler. That does not mean that there is no theory for the non-simply connected group, but it does create additional layer of difficulty and care. So I do not even know a very good general formula to deal with simply connected, non-simply connected, but semi-simple groups. So I'm not even sure in this case, is there a canonical central extension? So that's already a little bit of an issue. Is there a canonical central extension?
I think there is a paper of Ueno where it's divided in two parts, and the second part is about the abelian conformal field theory, and he tries to deal with this case with the torus. And he relates it with the Jacobian, so he's able to show that the dimension of these conformal blocks are correct, but the definition is much more complicated.
Oh, is that right? I see.
And I don't know if I think about the vertex algebra side of the story, you have the Heisenberg vertex algebra, which is very badly behave.
Oh, is
But
that
then
right? In what way is it very
it's not
badly?
rational.
It's not rational.
But then
Okay.
you can take the lattice, which is
Yeah.
very better, which is a quotient. And
yes.
so I don't know if, so the lattice is more like you have a torus.
Yeah.
So
Yes, yeah.
I don't know if the lattice, my interpretation is the lattice is like the good version of the Heisenberg.
Yeah.
And so in that case, you should still have.
Yeah,
it's
I think this should
rational.
match with the lattice
And then
one.
it's rational, and then you still have this construction, but you have to modify in the same way in which when you take the affine algebra, you have to quotient out by the maximal idea to have an integrable module.
Right.
Otherwise, it's not irreducible.
Yes.
Also, in this way, you cannot. The construction of the vertex algebra, it's much more complicated to describe.
That is my understanding too. I mean, I've never really looked.
There is a paper of Ueno which is divided in two parts. The second part, he developed this part with the abelian case, so with the torus, and he says also. I think Tsuchiya was working on this. He's not credited as an author, but he said this is work with him.
Okay. So he has a paper, you know.
Yeah, it's one. Okay, I can find it and send
Okay,
it.
no, that's fine. So yeah.
It's an old paper.
Okay.
Where he does, it's one of these version of TUI papers, but it's only by Ueno. The first part is the usual part, but then the second part is the abelian.
I see.
Part.
Okay.
But it's I don't know.
Yeah, I've never looked seriously at this
so the
one.
definition of conformal blocks is not the usual like coinvariants or maps, but there are extra conditions, which I think it involves saying you don't work with the Heisenberg but with the lattice, and so you have to consider more invariants.
Okay, so my plan today is the flat projective connection. So that's what I am aiming at today, to prove the existence of a flat projective connection. So let's carefully do the construction. So the first object is, which I briefly talked earlier, maybe even in my first or second lecture, family of S-pointed curves with parameters, with local parameters, with formal parameters. That's so this is sigma t, p, and T. Okay, so what is sigma t? So T is a smooth variety. So that's the parameter space. And sigma t to T is a proper and flat morphism with fibers, curves as fibers. And we require certain things as with reduced curves. And then we also have mutually non-intersecting sections, PI. So these are sections. So let's call this map I, and PI will be a map T to sigma T. So these are sections. And mutually non-intersecting, that's also the image. So PI T I is disjoint set of points. And we also require local parameters. Right. So And so this has as a consequence, sigma t to t is a smooth morphism in a neighborhood of PIT union. Okay, so I should say that. So, and P, yeah, okay, I have not said that.
So sorry, we're making this connection. Are we going to be concerned about the case where the curve is acquiring a singularity?
Not for this definition, okay. But next, yes.
Okay.
I will come to that.
So you're going to say something that includes the boundary.
Yes, that's right. Right now in this definition, but for the connection, I'm going to use that I don't, so no curve has really a singularity. Okay. So for definition, I don't need that. Okay. And actually it will be needed subsequently when I generalize the result to a situation when it acquires singularity. And what I require, right, and I should have said that. And this sigma B and PB is a S-pointed curve for all B. Let me write it and then I will explain it. Yes. And so this is B sigma T0 to T is an affine morphism where sigma T naught by definition is sigma T minus union Pi. Okay, and finally, I require formal local parameters Ti along the image T. So that is the formal completion so this will be O of sigma T and PIT. This is the completion of sigma T along PIT satisfies this one. Is right, OT power series. Right. And this isomorphism comes from the map OT to O sigma T to O sigma T. Okay, so I think I have completed the definition. Let's go over this. So by a family of S-pointed curves with formal parameters, we need a parameterizing smooth variety. And sigma T to T is a proper and flat morphism with reduced curves as fibers. Now, mutually non-intersecting sections Pi such that this sigma BPB is a S-pointed curve for every P. And S-pointed means two things. One, that these points are smooth. These are smooth points, and they don't intersect. And finally, every irreducible component of sigma B at least has one point coming from PB. So that's the requirement for a S-pointed curve. So to repeat, every reducible component should have at least one point, and these are smooth points. The PB are smooth points, and they are non-intersecting. So since these are smooth points, sigma t to t will be a smooth morphism in a neighborhood of this one, because these are smooth points. Now, the second requirement is that the sigma t naught, which is I'm removing these sections, this should be an affine morphism. And finally, we are making a choice of formal local parameter ti along PIT. That is, in the formal completion of sigma t, we have this isomorphism. And there is always such a choice locally. We can always choose locally a local parameter. But for what I'm going to say for the connection, I need to make this choice. And the connection will depend upon this choice. Okay. Right. So now I also need to shiftify all the other notions we have talked about. So lambda 1 through lambda s will again be some dominant integral weights for the affine Lie algebra. So these are the weights. And these weights do not change with the point. So on every point of the fiber, I'm going to take the same point. I mean, the same set of weights. Okay, so definition. So h lambda t is nothing but h lambda. And I tensor with the structure sheaf of t. So I'm sheafifying all the notions which we have done it point-wise. And now I'm going to define this this Lie algebra, and this is by definition G tensor OT Ti. And I take sum over I, and then plus OT of the central element. So again, I've sheafified the corresponding Lie algebra, which we had talked earlier, G hat S. So this was nothing but G tensor C T, I mean Ti, I from 1 to S. And then we took single central element. And the definition of bracket was you take the point-wise bracket here, and for the central charge, you add all the central charges from each factor. So we are going to do exactly the same thing. Okay. So, and now, so yes, third, we take G hat of Ft. So this is by definition G tensor pi naught star of O of sigma T0. Okay, so let's go over that. So I'm taking G tensor pi naught star. So pi naught is this map. So where pi naught is restriction of pi to sigma t g. So that's what it is. So now I'm taking the push forward of this one under the structure sheaf of sigma t0, and that is the map. Now again, this is the sheafification. See, earlier what did we do? So earlier, what we did earlier, that we just took one point and we had G tensor C of the curve minus P. Earlier, that's what our definition was, that we took this G tensor C minus the affine coordinate ring of this, and this is what was used in the definition of conformal block. So I will come to this in a minute. Now this embeds inside GT hat S, where GT hat S is this one. And what it does is that I just take X tensor F here. and I just map to X tensor F and Ti. Yeah, I mean, with respect to the parameter Ti or Pi, I'm just going to take that. So this is the map. And finally, the sheaf of conformal blocks. So sheaf of conformal block, and let's use the, so V of Ft lambda. This is by definition so this is by definition, I take H lambda T and divide by the action of H lambda T. I need to explain this. So H lambda T is just the sheafification of the representation. And now G hat Ft is this Lie algebra under pointwise bracket here. And this embeds here via this map. And by the residue theorem, this is indeed a Lie algebra homomorphism. And what we are doing now, that GT hat S acts on this one. Yes, so observe that GT hat S acts on H lambda T. So H lambda T is a representation for this one, where I just map it component wise, and everything is OT linear. So this acts on OT linearly. Basically, what I'm doing, I'm changing my complex numbers to OT linear maps. So nothing delicate about that. And just to put this in perspective, if I take this T to be 1 point, then this is our this Lie algebra. So this will be exactly our this Lie algebra, and the space of conformal block was by definition V of curve C. Actually, I used the notation sigma earlier, so why not I use the same notation? V of sigma P lambda was by definition H of lambda divided by exactly this one, G of sigma minus P acting on H. So this is the direct sheafification of this space. Now, so that's the definition. And now this is indeed sheafification because of the following. So let me put this as a lemma. So clearly, and let's tensor at a point B. So for any B in T, if I tensor this, this is clearly H lambda. And if I tensor this Lie algebra, this is clearly the Lie algebra, what earlier we denoted by G hat S. And most important thing is that if I tensor this conformal block, is isomorphic with V of sigma P of P and lambda. And Yes. So sigma B is the fiber over B. So sigma B. Okay. So this lemma, which is actually quite easy to prove, this is not a delicate lemma. So this says that the construction we have made is indeed like a genuine simplification of our earlier construction. Now, so there is a lemma whose proof is more or less identical to the proof which we gave earlier, that this one, V of Ft P lambda, is a coherent sheaf of OT models. See, earlier we proved that the space of conformal block is finite dimensional. And basically, it's the same proof. That proof required our Lie algebra to be over complex numbers. Now you replace that with this OT free Lie algebra. So this GT hat S is an OT free Lie algebra, and you replace that. And the main point is that the decomposition of a Lie algebra is available for free Lie algebra over any ring. The Poincare-Birkhoff theorem. So PBW theorem is valid over any ring as long as, I mean, over any, let's say, commutative ring, I should say, as long as commutative R, as long as this Lie algebra GR is free over R. And that is the main ingredient in the proof for the finite dimensionality of conformal block. And there we dealt with Lie algebra over complex number, and now we will deal with the Lie algebra over OT. As long as it's free, we can use the PBW theorem. Okay. So now I'm going to come to the connection part. And to define the connection, it's really coming from the Virasoro algebra. That's where the connection is coming from. So we defined the Virasoro algebra, and I don't think I need to define it there. But I'm going to sheafify Virasoro algebra. Okay. So what is sheafified Virasoro algebra? So I'm still going to do over T. So I'm going to define a Virasoro algebra over T, but in S many variables. And this is by definition, I will take OT of Ti, and I mean, this right now is just a symbol. And then a single OT C bar. Okay, so Virasoro algebra over T in S many variables is by definition, we take OT of Ti and partial Ti, and then add one central element. And the bracket, let me write down the bracket. So if I take, okay, so any element I can write it as Fi dti, and let's say Gi dti. Okay, So the definition is just do the bracket as if these are vector fields, which actually they are. So I'm going to do Fi, partial Ti's, Gi. So Gi, Ti. And then I'm going to do the other way around. So minus Gi, partial Ti of Fi. And then I stick in Ti. Well, actually, I've used, let me just keep this short. And then we have to add the central charge. Okay, so that's the non-central piece. And the central charge is I from 1 to S residue at Ti equals 0 of this function, dTi cubed F I G and C by 12. Okay, so let's see. So what are we doing? So we take the usual derivative of vector fields. I mean, usual bracket of vector fields. So that's this part. But then we have to add the central charge. We say I'm taking residue at Ti equals 0, the third partial of Fi times Gi, and take the residue at Ti equals 0, add them up, and we multiply C.
Is there a sum in that first term?
Oh, you're right. Yeah. I mean, I should really say direct sum. So it means that in the ith factor, this is the term. Does it make sense?
No cross terms?
No cross terms. No cross terms. No. Exactly. And just keep in mind that even for the affine Lie algebra G hat S, there were no cross brackets. Only the bracket is taken in individual factors. Yes, absolutely. There are no cross terms. Okay, so now, let's make one remark here. That if we take S to be 1, and let's see, what do we take? And Dn to be minus t to the power n plus 1 dt, and t equals spec c. Then is our old philosophy. So if we take S to be 1, only one factor, and if I take Dn to be negative t to the power n plus 1 dt, and t is spec c, then this very Ts is our old pair with the basis. Dn and Nz union C. Okay. Any questions so far? Okay, so now I'm coming to, okay, so what do I do? So I am going to give an OT linear action of Virasoro Ts on H lambda T. So this is the Sugawara construction. So the last time we did the Sugawara construction for just Virasoro for a point on H lambda. And we are going to extend that construction to this setting where we allow OT. Okay, so first of all, C bar acts on H lambda by the constant by C times dimension of G divided by C plus H check, where H check is the dual Oxford number. So C bar is acting on H lambda T by this constant. And this is exactly the constant which C bar was acting on H lambda without T and a single factor. This was exactly the constant. And we are using the same constant here. But the more delicate thing is how does this, if I take f ti to the power n plus 1 delta ti, how does it act? So here, right. So let me write the answer and then we will. Okay, so I need to explain the notation here. So V is V1 tensor Vs, and Vi is in H lambda I, ith factor, and what is F is in OT.
Sorry, oh yeah.
Say it again?
No, it's okay. You just explain.
Yeah, right. So, and so OT linear action and extent by OT linear action. Okay, so let's go over that. So any element of the Virasoro by definition looks like OT Ti delta Ti. So I'm taking f of Ti to the power n plus 1, and that can be negative. So n is any integer. Delta Ti will act on a vector V from this tensor product of representations by minus f divided by C plus H check. C is our fixed central charge. And I am only acting, this ith factor will only act on the ith factor. And this is the usual Sugawara action. So this is the usual Sugawara action. I'm only acting it on the ith factor because I'm only taking I. And if I take arbitrary I here, then of course I act on arbitrary I factor. So, and it is manifestly OT linear because this F comes out as F. And I only define this action for V in not the actual H lambda I, not the OT tensor, but you just tensor it with OT and take that scalar out. So that's the action. Okay, so now the point is, so a word of caution here. So I'm going to denote this action of with ST on H lambda T by okay, mu of lambda. Yes. Okay, so this is not a Lie algebra action. So I'm giving you some action, but it's not a representation of the Lie algebra Vir ST. Okay.
Sorry, why not?
Right. You see, because the Sugawara action is not a Lie algebra action. So there is a factor there. You see, ln.
Right.
And that creates not a Lie algebra action. You see, in fact, I will tell you the precise commutation relation. Let's see if I have that. Yeah, so the precise. Yes, it's here. Okay, so
I think I had just taught the action of the ln.
Yes, exactly.
On H lambda.
That's right, exactly. And that's not a Lie algebra action.
So what is it?
The ln is, so we had this map from Vir to the universal enveloping algebra of GHAT,
Yes.
right? But didn't we divide by the factors so that?
So you see the commutation relation is, so see, that's what will be manifested. It's a projective representation.
But doesn't the C fix that? That's what I'm good.
Okay.
The C bar, isn't that designed to make it a real representation?
Okay, let's see.
Sorry, the more basic question. So even if you have only 1 point, that's not.
Yeah. No. The trouble is already in 1 point. The trouble is not there for arbitrary number of points. The trouble is already there in 1 point. Okay, so yes. So how? So what is the commutation relation? So so yes, so I have the computation relation. So ln is C plus H check, then m minus n, Lm plus n, plus delta m minus n, m cubed minus m by 12, dimension g. And then I have C plus H check. Okay, so that's the computation relation here between Lm and Ln.
Yes.
Okay, so right. Whereas the Virasoro, yes. So now see what I'm doing. Basically, I'm dividing by C plus H check.
Yeah.
Okay. So if I divide by C plus H check, this goes away. And we have C plus H check. And then we have C plus H check. So this goes away and we have C plus H check. Right? Okay. So okay, so here there is now the Virasoro action was, let's put it here, dm dn is m minus n dm plus n plus m cubed minus m by 12 delta m minus n and c bar. Okay, so if I do that, so Tm Tn m minus n Tm plus n, so that's exactly what Tm delta m minus n m q minus. So c bar is c by c plus h times g. So c bar acts on this with the correct one. So this seems to be no, this is definitely not a Lie algebra action. I know that. Why is it not a Lie algebra action? So,
but I thought it was a Lie algebra action, but it's just not component-wise derivation as you would like it to be.
No, it's not a Lie algebra action. So if you so it is not a okay. Okay, so okay. No. So no. So far this is okay. This is no. This is a Lie algebra action so far.
Okay.
Right.
Sorry. In your book. Yeah.
Yes. No. Sorry. So far this is Lie algebra action. But we need something beyond that, which will become manual. Okay, so I did not remember it correctly. So this computation shows that this is a Lie algebra action.
Yeah, I think it's like an action of the affine Lie algebra semi-direct product.
Yes, exactly.
Yeah.
That's right. That's absolutely right. So this is an action of the affine Lie algebra semi-direct product with the Virasoro algebra. So far this is correct, but next step it will break down. Okay, so I did not remember it correctly. Okay, so let's see. Unfortunately, I will have to let this go. Yeah, so let this go. Okay, so now I'm going to do the construction of connection. So that's what I'm going to do. So just as above, let Ft and then P and T be a family of S-pointed curves with formal parameters. Algebra. But now we require this pi map sigma t to t to be a smooth morphism. So that means that now sigma t, since it's a smooth morphism and I'm assuming t to be smooth, this will become smooth and all the fibers will be smooth. Okay, so we introduce this notation sigma t 0 to be sigma t minus union PIT. Okay, so let theta sigma T0 be the sheaf of vector fields over sigma T0. So I'm taking the sheaf of vector fields over sigma T0. So for any, let's say for any in this one, we can write so actually I would keep I would just like to keep this isomorphism. Okay, so so we can write theta check equals theta check, all right? So, and theta I check H in a neighborhood of a single PRT for any. Okay, so what is the property? So theta I tilde H is horizontal. So that is theta I tilde H on Ti is 0. And theta I naught, this belongs to OT Ti and delta Ti. Okay, so I am making this decomposition. So I'm right. So we take a vector field here, and the point is that locally, yes, sorry. So this vector field, locally I can decompose into a horizontal vector field and a vertical vector field. That's what I'm doing. So this vector field, I write it as theta I tilde 0, which is horizontal. That means that at Ti it is 0. So Ti is the vertical thing, and theta I tilde thing lies here. And this is happening only in the neighborhood of PIT. And this is because of this decomposition. So this thing, it is here. And mind that this vector field is only defined on this open part. It's not defined on whole sigma T. So this acquires pole along PIT. So this vector field is acquiring pole along PIT, and that's what is reflected here. I take OT, not the power series Ti, but the formal Lorentz series Ti. So we will have that decomposition. Now, let's remark that this decomposition does depend upon the choice of the local parameter. So if I were to choose a different local parameter, I will get a different decomposition like that.
So I'm still trying to parse this.
Yes.
This one is horizontal and the other one is what?
It's basically vertical. I'm writing it in terms of a horizontal vector field and a vertical vector field. Something is
Confusing me then, because the horizontal condition appears to be only at the point Ti.
In a neighborhood of the point PIT.
So what is the formal definition of horizontal?
So only along Ti it's 0. So it will have X coordinate along PIT.
It kills the tangents. It kills
Yes.
the tangents to that section of points.
Exactly. That's right.
Sorry.
Okay. So
my confusion is if the horizontal condition is something which is being imposed just along the section.
Yes, that's right.
But then how can you decompose in a neighbor? So I understand if I split, everything is horizontal plus vertical. Right. But horizontal there is a condition not just along a section, but in a neighborhood of the section.
That's right. Indeed.
So is your horizontal, maybe I'm misreading the notation, but it looks like that's a condition just at the section.
So you see,
Oh, that is considered as a formal function of Ti.
Exactly.
Okay.
Exactly.
Okay.
That's right.
Okay.
That's right.
Okay, then I'm happy. Okay.
That's exactly right. So I'm just saying that if you take the component of this vector field along Ti direction, there is no component. That's all I'm saying.
Yeah.
Okay. Now that's right. So that's where comes this non-linear algebra action. Okay, so that's actually maybe some of the definitions I would need. Oh, actually, let's keep this. Okay, so now we get an OT linear map. Data from I naught star of theta sigma T0 to where ds. And what it does, so I take a vector field here and I map it to this one. Okay, so let's look at this map. So I am taking a vector field theta check here. I mean, this is just the direct image of that. So I want to make it OT linear. So I take theta twiddle and I'm mapping it to theta I twiddle is 0. So this is here. So just the vertical component of that vector field I'm taking. So this is, now keep in mind that theta I twiddle is 0 is an element in OT Ti delta. That's where it is. So that means that this is a genuine element in the Virasoro. So I define this map. Now this map is not a Lie algebra homomorphism, right? So I got a little confused there. So beta is not a Lie algebra. Because this has its usual bracket, the bracket of the vector fields, but this map is not a Lie algebra homomorphism. So now this implies that we get an action of pi naught star of theta sigma T naught on H lambda T. That's what we get.
Okay, so that's the one which is only projective.
Right, exactly. So I was wrong earlier. And I am going to denote this action. So earlier this action I denoted by nu of this one. And I'm going to denote this action, which is not a Lie algebra action. So denote this action by nu of lambda. And I will put some height here. So this is what I'm going to denote it by. Okay. So now I am almost ready to define the connection. Okay. So I suppose I don't need to define a projective connection of a bundle. So projective connection on a vector bundle is nothing but a connection on the corresponding projective bundle. It's a PGL connect. Okay. So let's actually, it will be good to have this definition here. So I'm just going to use this part of the code. Right. So definition. So let V over T be a vector bundle. Then by a projective connection, I mean a PGLN be a vector bundle of rank n. We mean PGLN connection on the corresponding projective bundle. Okay. Now, so that's what we are going to construct. And this is equivalent to saying that we can take an open cover of T and a usual connection there on the vector bundle such that the difference of connection on the overlap is scalar multiple, is a scalar operator. So delta I minus delta J equals a scalar operator. So if I take it, on the phi by P.
So can you?
1 minute, let me write it for all P in T and V in tangent space of T. Yes.
So in this case, I guess you would expect that, is this right, that if you twist the bundle,
yes,
by some power of the Hodge bundle, you get a flat connection.
But the question is from to reality.
Reality in which?
A sense that suppose I take a family,
yeah,
and I pull back this family,
yeah,
okay, to some other parameter space.
Yeah.
Is this connection?
Yeah, I think I'm just asking, is
yes,
there a refined statement of the nature that rather than giving a projective connection, gives a connection on the twist of this by some power of the Hodge bundle?
You'd expect. And Hodge bundle means the top form?
The bundle, yeah, whose fiber is the determinant of top form.
That's right.
Yeah.
Yes. I really doubt it. I really doubt it. Even though I would not say a definite 100% no answer to your question, but I really doubt it.
Okay. But I can think of this also as a connection with whose curvature is a scalar, right?
Yes, of course. Oh, of course.
Okay.
See, because exactly the curvature is a scalar. That's right. That's right. But you see, here's the point. Now I can answer this. So curvature is a scalar, right? Now, if I tensor this with a line bundle,
yeah,
unless that line bundle also has scalar curvature,
yeah,
I would not kill the curvature.
Right, but I think when you say scalar, it means okay. I think it has the same curvature as some power of the Hodge bundle. That's why I thought you might be able to.
So you are saying the curvature is.
Sorry, we don't need to. We can talk about it later. It's a bit off topic for your thing.
Actually, I tell you one thing. This bundle does not even admit a connection. It only admits a projective connection.
Yeah, but I only want a connection after twisting it.
But I think it's probably true. But you know, the paper of Tsuchiya-Ueno, when he constructs, he defines this connection.
Yeah.
And he describes explicitly the Tsuchiya algebra.
Yeah.
So it's the same as saying there is a central extension of your tangent bundle that acts instead of being the tangent of acting. And I think if this extension comes from line bundles, like differential operators on line bundles, then you can twist by the appropriate thing. And I think this is how the way in which I think about this projective connection is that if you're not on T, but on appropriate covering of T, then you really have a flat connection. And then in the descent process, you see that you cannot, you fail to be.
No, but see, when you descend, see, you pull back the vector bundle, and now you descend. You are not going to get the same vector bundle.
Well, but I guess the way in which one can define the conformal blocks, like we fix coordinates, but if you want to forget the coordinates, like this is how we can define, like there are different versions in which we can talk about this, the conformal blocks, right? It can be coordinate dependent, or it can be coordinate independent, or it might depend only on the one jet, on the the tangent direction.
That's right.
And this corresponds to different levels of descent for getting the coordinates. And if you really always fix a coordinate t, then I think there you can define a connection, which is really not projective. And in the descent process, you lose this, the well-definedness, like the bracket doesn't work because you're forgetting some information about the coordinates. And I think you can keep, if you twist by appropriate powers of the line bundle given by the central charge, and also, so if you first descend to the jets, you have to twist by what is the lambda to some power, and when you descend to T, you have the side classes to some powers of the Casimir operator, like depend on the representations.
Yeah, okay.
So there are different powers, different line bundles with different powers depending not only on the algebra, but also on the representations that you take.
No, I'm willing to do that, but so are you saying that suppose I have a vector bundle? I mean, let's ask the general question. Suppose I have a vector bundle and I have a projective connection there, which is projectively flat.
Yeah.
Can we always twist the vector bundle by a line bundle?
Oh, no, I don't think I'm saying. I'm just saying in this specific case, there's a natural line bundle, which is the Hodge bundle. And the curvature, I think, matches that. But sorry, this is way off here.
So, okay, I will have to think about that. I will have to think about that because at least the construction I'm going to give, it's not very clear that Hodge bundle will unwind it.
Yeah.
Maybe it does, but it's not clear to me, the construction. Okay. So, right. So I defined this thing. Now let's do the construction of the connection. So I want to, let's see, what do I want to retain? Right. So this. Okay, so let me first write the theorem that this space V of Ft P lambda. So this is the sheaf of conformal block, which is still there, admits so first of all, is a locally free OT module, which admits a flight projective connection. A flight projective connection. So I will denote it by delta Ft and lambda, which and further it is functorial. So functorial means that if I take another family which is pullback of this family, then this connection is fine. Okay, so let's put this. So we need to define. So what do we need to define to do the connection? So first we are going to do, so delta V. So if I take any vector field, so I take a vector field on T, and so first I want to define for any, let's say H, where H is in H lambda T. Okay, so first we are going to define some operator, delta V from H lambda to itself. So first we are going to do that. So to do that, one has to do it locally. So this vector field V, so locally, V can be lifted locally in T. V can be lifted to a vector field let's say we twiddle on theta T, sigma T. Okay, so first of all, let's look at that. So one is claiming that locally in T, this vector, so I'm taking a vector field on T. That's the vector field on T. So V is a vector field on T. And locally in T, V can be lifted to a vector field V twiddle in theta of sigma T naught. So I can lift this vector field to sigma T naught. So we have a map sigma T naught to T. And so we have a vector field here. And this vector field can be lifted here. Lifted means that if I project it down, I get the vector field. And we can do it locally. In fact, we can do it as long as T is affine. So on an affine open set, we can do it. Now, do you agree to this statement? Are you all comfortable with this statement? Okay, very good. Actually, this is quite easy to prove. Just write down the corresponding exact sequence for the sheet. So the main thing here is to prove this, just write down this standard sequence for vector fields. So theta of sigma T 0, so theta of T to 0. I mean, I should write P naught star of sigma T. And then this is the vector field along the fibers. So this is the standard sequence, and this is the map d of pi j, the derivative of pi j. So take a vector field here, project it to the vector field on T, and the kernel is exactly the vector field along the fiber. So vertical vector fields. And this exact sequence will give rise to exactly this statement answer. Okay. So now I have to define this map. So delta V of H. So what is the definition? Okay, so I am going to write it in, so G tensor H, and this is by definition theta of G tensor with V plus G of this action we did for twiddle on V. So the notation here is G is in OT and H is in H lambda. Not H lambda T, but okay. So
you're calling, I think you're calling V theta.
Okay, 1 minute. 1 minute. Let's see. I have made some notational thing. Right, so this is theta. Is that what you said? And this is h now. Yes. And this will be h. Right. Okay, so let's go with this. So I'm defining this covariant derivative of this vector.
And the first G, sorry. The argument of theta should be theta, or phi of G.
Actually, I know why I made a change of notation
Yeah.
from my note to this one. And that's what it's called. Right. So I'm defining this. So this is delta V G tensor H. So this is by definition VG, derivative of G along V, tensor H, and G. And now I'm using this pullback, which is not unique. I'm using this pullback, applying on H. And this is the action which is somewhere. This one. So this is the action. So this is the action. Now, so what happens that, yes. So let's write down some properties of this. Okay, I think I don't need this anymore. So this delta V, actually I should really write it theta twirling right now because it depends upon the choice of the pullback. So it's better to put that in the notation. F times G tensor H is VF times G tensor H plus F times delta V twiddle of G tensor H. So that's one. But the more important relation is that delta V twiddle and the commutator with Y check H V twiddle of Y check as operators on H lambda T for any Y hat in G hat Ft. Now G hat Ft is here. This is G hat Ft. Yeah. So the commutator of this action. Now, okay, I have not told you. Did I tell you that how does this act? Something I need to explain here. Right. Okay. Yes. So, of course, delta V twiddle is an operator on H lambda T. Now, I have not told you how does Y hat. So Y hat is an element here, which is nothing but G tensor of pi naught star of O sigma T naught.
This is the action when you were defining the sheaf-ified conformal block.
Yes,
right?
that's right.
You already
exactly. That's exactly right. So that's exactly right. So that's how it's acting. Right. Okay. So this is a very important relation. Now this is some calculation. I will not do it on board, But this has consequence.
This is the fact that it's that the representation of the affine algebra extends to affine semi-direct.
Yes, exactly. That's exactly right. Absolutely.
Semi-direct what?
Virasoro.
Oh.
So see the representation on H lambda t, as Yaksha said, extends to a representation of Virasoro semi-direct product with the affine. Now this has the consequence that if I take delta V and I apply to G hat ft, G hat ft, on H lambda t, then it goes inside G hat of ft. H lambda. Right. And this is very important relation. So when it's saying that this connection, when I apply here, I land in the same one. Because I mean, I'm taking the commutator and I'm still getting there. So it's clear from this one that we have this one. Okay, but this, as you will see immediately, right. So this has the consequence, which let me write it. Okay. So I'm going to. So this means that this delta of V12, which was a map operator here, descends to on this sheaf of conformal blocks. Because the sheaf of conformal block, by definition, that's here, sheaf of H lambda t divided by this action. And then we prove that this one keeps intact. So we get this operator on this one. But now here, mind that this operator depends upon the choice of the lift. So the question is, how much does it depend upon the choice of the lift? So that's where the delicate point comes. So now we are going to do a curvature calculation. So I'm going to write it as a lemma, a curvature calculation. And this calculation says that if I take G in OT and H in H lambda, so then this curvature calculation of, let's say, V1 twiddle and V2 twiddle on G tensor H is G data of V1 twiddle, V2 twiddle. I will explain this notation in a minute. Acting on H, where this beta, V1 twiddle, V2 twiddle, is a function on T.
Sorry, so we can't just see directly that this is almost independent of the lift from the properties of some suitable like positive Sugawara operators, or?
Okay, it does require something more than that. At least I don't see that directly from there. But see, because see, that's where the projectivity comes.
Right.
That's where the projectivity comes.
Yeah.
So let me explain this. Maybe what you are saying is because this does not match up to give a connection, honest connection. It only gives you a projective connection. So in any case, this is a simple calculation for the curvature. So this says that the curvature is really a scalar operator. Okay, so the final thing now, so let's take two different lifts. And then what happens? So we have V, and now I'm going to take two different lifts, V1 twiddle and V2 twiddle, two different lifts. Okay, so this means that V1 twiddle minus V2 twiddle becomes really a vector field on theta sigma T0 divided by T. See, because they're both lifts of the same vector field at T. So the difference is going to be a vector, a vertical vector field. That's all I'm saying. Okay. Okay. So moreover, if I take any vector field here, so let's take a vector field. I'm just going to call it V twiddle, any vector field here. Then this delta of V twiddle is a OT linear operator. And that follows from the definition, you see. So if I take V twiddle to be a vector, vertical vector field, then it follows that this portion will go away because it's a vertical vector field, so it will be only this one. So that means that this delta V twiddle becomes a OT linear operator, right? Okay, so this gives me a map. So delta V twiddle B becomes a linear operator CB, tensor whatever this space is, VFT. Itself. But this is the space of conformal block at the point B. So this is a finite dimensional vector space, right? Okay, so let's see, what do I want to say next? Actually, I'm coming to the last part of this proof. Okay, let's see, what do I want? I think I can erase this. So if I organize this delta V twiddle, then I'm going to get a linear map. So fix B in T. Then I'm going to get a linear map, delta B. And this is from CB. And this is pi naught star of theta sigma T0 over T. To endomorphism of CB tensored with OT of VFT and B. So let's see if you agree to that. So I am taking any vertical vector field here. So I take any vertical vector field at the point B. And now, see, because this delta V is a OT linear map, this gives an endomorphism of this one, of CB tensor. So this gives an endomorphism of this one. For any vertical vector field, I get one endomorphism. So I get a map like that. And right. Moreover, so this delta V is a Lie algebra homomorphism on the corresponding projective. Projective representation. On the corresponding projective space. Right. Okay. So let's go over this. So we get such a linear map here. And I'm saying that this linear map actually is a Lie algebra homomorphism. Now this, of course, has the standard Lie algebra bracket, vector fields. They are vertical vector fields, so they have a bracket, standard bracket. And now, if you look at the curvature result, the curvature is exactly the deviation from this to be a Lie algebra homomorphism. After all, the definition of curvature is that delta V1 twiddle, delta V2 twiddle, minus delta V2 twiddle, delta twiddle, minus delta V1 twiddle, V2 twiddle. That's exactly the curvature. So the curvature gives you exactly how much it deviates from being a Lie algebra homomorphism. And since it's a scalar operator, delta B is a linear Lie algebra homomorphism on the corresponding projective space. Okay, right. Now this is happening at every B. Okay, so there is one thing I will not prove here, which is to be proved independently, that this sheaf of conformal block actually is locally free. Of course, once it has a connection, it becomes locally free. But actually, I need to prove it beforehand. And that comes from this operator. Because if it's not locally, so you take some generators here. And if it's not locally free, there will be some relation at some point. And then you apply this operator, and you will get a relation in a smaller degree. And so basically, you go through the proof of why a vector bundle which admits a connection will be locally, no. You take a coherent sheaf with a connection. If it admits a connection, it's locally free. You use exactly the same proof. Even though this is not exactly a honest connection, still the same proof will work to decrease the degree of the relation. So we prove that it's locally free. And once it's locally free and this condition holds for every B, so this implies that that delta V, delta V twiddle acting on the sheaf is a scalar.
Sorry, where did that come from?
For 1 minute, let me write. For any V twiddle in the vertical vector field. Sorry, Akshay.
Where did that implication come?
Okay. So what we proved that delta B, once it's specialized to it. So think of this as this is a vector bundle.
Yeah.
This is a vector bundle. Yeah. And at every B, this thing becomes a Lie algebra homomorphism modulo the scalar.
Yeah.
So now I'm saying that delta V acting on this is actually a scalar operator because at every point it's a scalar operator.
So why is it a scalar operator?
Scalar operator, scalar does not mean constant, it's OT operator, OT. So delta V twiddle is so some function f times identity on the projective one.
So it's, yeah, I don't see, why is it a multiple of the identity? There's something to be proved at each point, right?
Okay, so
so these functions come from the local Virasoro.
Right.
And somehow you're saying if it comes from global Virasoro, it's trivial on.
Exactly, exactly. Absolutely. So here is the result, which I have to explicitly mention. Right. That's right. Exactly. So there is this result by Verlinde. Yeah, so let me write this result. Actually, I classified this thing point fading measure. So let C be, I'll just use sigma, be an affine smooth curve. Okay. Okay, so then phi naught star theta sigma T0 over T is a finite direct sum that's of infinite dimensional simple algebras. That's the point. That's the missing link. Okay, so let's go over this. Actually, I don't need this. I mean, I have already set up the notation, so I don't need this. So I'm saying that let's take these vertical vector fields.
I see.
So let's take these vertical vector fields and specialize at a point P. Okay. So this is a finite direct sum of infinite dimensional simple algebras.
In the case of A1, I would get the biology.
Yes, exactly. That's exactly the point. So this is more general result than that. And it says that it's always a finite direct sum of infinite dimensional simple algebras. And now I'm just going to apply this here. So this is now a infinite dimensional algebra, which is direct sum of simples. Simple infinite dimensional, but this is a finite dimensional space. Right? So the kernel has to be the whole thing up to scalar. So that's what it. So this becomes really a scalar operator. Not only it's a projective representation, but it's a scalar operator. Right? Are you all comfortable with this? Yeah. So this is very important, at least in this schema proof. So now it's a scalar operator. Now I can patch it up because what we proved that this delta V twiddle define an operator on the sheaf of conformal block. But if I take a different lift, it's only going to differ by a scalar. A scalar means OT scalar multiple. So if I do the projectivize this thing, I get an honest connection, not depending upon the choice of the lift. And this connection is flat, that already comes from this calculation. So that's the proof.
So this is an interesting global ingredient. I doubt this is very hard to prove, but it's some sort of not. It's a different type of argument.
Exactly.
Yeah.
That's right. Exactly. But somehow this is kind of a crucial piece.
Right. I think maybe the physicists would define conformal blocks differently by quotienting by more things in such a way that, but it wouldn't be obvious that it was
It's the same object.
For just the affine Lie algebra. Right? I'm not sure, but I think if you look, they would, a priori, they would be quotienting by more, and it's only at this point that this is because of some argument like this one that we know that. I'm not sure, but that's because I don't think in the physics literature they have any argument like this one.
Right.
But I think
definitely not.
But I think it's absorbed by the definitions being different.
Yeah. Actually, even in this original paper of TUY, Tsuchiya-Ueno-Yamada, I don't think he has this argument. And in fact, some of the arguments in his long paper.
Oh, they had some different argument, is it?
Well, yeah, they have some different argument, except that, see, I am working with arbitrary family, right? I'm not working with a specific family. And they are only working with the versal deformation. So they are working with a very specific family, versal deformation, and they need to use some property of the versal deformation. The deformation map is surjective. And and I don't think that they are using this result which I mentioned. Right, I mean,
it's a nice argument.
So, I mean, yeah, I thought of this argument to avoid just using, I didn't like to just use one particular deformation of the curve.
Yeah.
I mean, I wanted to do it in general too. So this argument seems to work. So that finishes, and functoriality, this whole construction is very functorial. So that's how, yes.
With respect to what?
So, right. So functoriality means that I have a family over this one, right? Now I take another map and I pull it back this family. So it's a smooth family. And then you can ask if this connection will pull back to this connection. And it will, because the whole construction is very functorial in this OT. So that's how the proof goes. Actually, I am a couple of minutes over time, and I didn't give you any break today.
So you're here, we have one more lecture, right?
Yes, we have one more lecture.
2 weeks, is that right?
That's right, because next week is Thanksgiving.
Good.
Now, I really, okay, so let me tell you the plan next week. So this local freeness, we proved in this, not proved, but at least I told you enough argument that you can patch it up. But we want also this local freeness in a family where some curves are allowed to have acquired in Beauville. And I'm going to say something about that in the next lecture. And then I'm going to use this algebraic machinery to go from arbitrary genus to genus 0 with 3 points, and then the fusion rule takes over. So I am going to, I think, give enough argument to at least give you this part of the picture, let's just call it Lie algebra proof of the Verlinde formula. But then there is this whole, at least from my perspective, even more interesting part, going through this moduli space of G bundles and vector bundles. And there is a very rich theory there. And I wanted to say something, but I don't think I will have time. So, and in fact, I tried to check if I can sandwich some lecture next week before.
We can do on Thanksgiving. No.
Yeah, but I mean.
We're giving thanks for having no lectures.
Yeah, exactly. So I talked to the secretary that can we sandwich some lecture between Monday, Tuesday, and Wednesday. So she gave me 2 time slots. Both of them, I don't think you will like. One was 5 o'clock onwards, 5 p.m. onwards, and another was too early in the morning. So both of them will be so, yeah. But in any case, that's what.
Okay, thank you.